So I'm going to talk to you about Chapter 13. This is the repeated measures ANOVA. We just did the Chapter 12, the independent ANOVA. So it is like the independent ANOVA. It's one IV with 3 or more levels. The difference is that it's the same people in each condition, so you don't change people. So you can follow people over time or through therapy, whatever it may be that you're measuring. The nice thing is also that it's 90% the same as the independent ANOVA in terms of how you calculate it. There's some small differences which I'll point out. And the F ratio is similar. The numerator is identical to the independent ANOVA. It's MS between treatments, but the denominator will be different. It's MS error because we have to remove any variation due to the participants. So we can have the same kind of questions that we've had with other tests. So do the scores change over time with practice? So our independent variable is practice, maybe the hours of practice, 1 hour, 2 hours, 3 hours, and scores is our dependent measure. So here I've got some data. The independent variable is practice, and I have chosen the levels of 0 hours, meaning essentially they have not had any practice, and 1 hour and 4 hours. So you have to be careful if you're making your scale that these are, although it's a ratio scale, you have to make sure you're spacing it out correctly to represent the correct amount of time passage. So this is really person over here, A, B, and C. So the scores here are all from the same person across the columns, which is what makes it the repeated ANOVA. So what I've done here so far is the data summary that would also be exactly the same for the independent ANOVA. I just wrote down the n values under each set. Of course here there's no possibility of them being unequal because the same people have to be tested across the 3 conditions or any number of conditions you have. T is the sum of x for the treatment. Then there's sum of x squared, t squared over n, which is going to be part of one of the formulas again. But if you have sum of x squared minus t squared over n, these two, you get SS. So it's an easy way to get SS, which you will also need the formulas. And then the m, although it's not used in ANOVA, we will use it to plot the data. And then this is a G, and no, it doesn't look like one, is 43. It's the sum of the t values. Capital N is all the data points. So we have 3 in each condition, so we have 9 data points. And then K is the number of conditions. There are 3 in this case. So we're going to add one more column here, and I'm going to put a line so I don't think that it's another condition. And it's going to be P, and it's summing across for each of the participants. So I'll do that. So I've added the P column, which is just summing across for the participants. So 3 plus 4 plus 7 is 14. And then 19 and 10, we only have 3 participants here. And then just like we did the t squared over n, we're going to do p squared over k, because that's going to be part of the formula to figure out the variation due to the participants. And that's it. That's the only additional step that you would do in the repeated ANOVA. So it's a pretty good savings for that test. It's very, very similar as compared to the independent and repeated T. Step 1, you have the experimental hypothesis. The symbolic is at least 2 means will differ. You have to find one difference there. And then there will be an effect of practice on scores. And the null is mu1 equal mu2 equal mu3. They'll all be the same, so there will not be an effect of practice on scores. So now we're doing step 2. You have to have the alpha level, and then what I've got listed here are the 3 degrees of freedom needed. For the independent ANOVA, you use these first 2 to find the critical value in the independent ANOVA. So DFBT, which is k minus 1, the number of conditions minus 1, and DFWT, which is based on the participants, is n minus k. So we had an n of 9 minus 3, we have 6. And DF total is big N minus 1, so we had 8, and you'll see that the 2 of those add up to that. So I've done 2 more degrees of freedom over here. We have DFBS, or between subjects, which is n minus 1. So we had 3 participants minus 1, so we have 2 degrees of freedom. DF error then this is the first place we're actually subtracting out variation due to the participants. DF error is DF minus DF between subjects. So 6 minus 2, and we get 4. So these two are components of the within treatments. So you see 2 and 4 equals 6. But we're going to use this one for the critical value and this one. So we want a critical F of 2, 4. Remember, F is a positively skewed distribution with your critical region being only in the one tail. You don't have to worry about directional tests. You go over 2 and down 4 on the F distribution table, and then pick the light face type for the 0.05, you find the critical value is 6.94, which is right here. So the first equation we're going to do is the SS between treatments. This is exactly the same as the independent ANOVA. Sum of t squared over n minus g squared over n. So I've taken the t squareds over n that we did in the data summary. They're right here. And I've added them up to get 228.33. And then g, which is 43, we're going to square that over n, so we get 205.44 to end up with 22.88. SSWT, which is sum of SS inside each condition. So again, that was from our data summary table. We have the SS values. We had 4.66, 2, and 8. And all I've done is add them together. Pretty simple. So I've done now SS total. And I don't think I added up the sum of x squareds on the data summary, but when you add up the sum of x squareds in each condition, you get 243. So that's for the entire data set, minus the g squared over n, which we did previously. So 243 minus 205.44 gives you 37.56. I think there's a slight rounding error somewhere, but we have, if we add the SSBT and SSWT together, they should add up to this value, and that's a good check. What I've calculated here is SS between subjects. So just like SSBT is related to the treatment effect, SS between subjects is related to the variation due to the participants. So we sum up the p squareds over k, which were on the data summary page, and then we subtract the g squared over n. So we get 13.55. So then what we do is we find SS error, which is now we're actually physically subtracting out the variation due to the participants. So SS error is equal to SSWT minus SSBS. It's very similar to the way we did this in the degrees of freedom in step 2. So we take our 14.66, which is SSWT, and subtract 13.55, and we get 1.11. So this is the value that's going to be used to go forward for the denominator, and this value is the same as in the independent. It's going to go forward for the numerator. So here we have the numerator of the F ratio, MSBT. It's SSBT over DFBT. So we plug in the values from the SS of 22.89 and divide by 2. So we find MS error, which is the variation in the denominator. SS error over DF error. Again, remember, you use your subscripts, so you're going to get lost. 1.11 over 4, we get 0.28. So you can already see that the variation between treatments far exceeds any variation within the conditions. So we end up with F of MSBT over MS error, the two values from here and here, and we get an F of 40.86. It's clearly a very large F. Remember, F should be about 1 when there's no treatment effect. The numerator should equal the denominator. So step 4, you report the F as it would look in a journal. F2, 4 is 40.86. P less than 0.05, it's out in the critical region. You reject the null, and you say there is an effect of practice on the scores. Now we're not quite done, because we will need a post hoc, because we rejected the null, and I'll show you effect size and also how to graph the data.